work to enhance the quality of intellectual life at Franklin and Marshall College. His dedication to faculty development stemmed from the belief that instructors who truly engage in scholarly endeavor will be in the best position to inform their teaching with fresh insight and renewed enthusiasm. He played a pivotal role in the professional growth of members of the faculty by encouraging them to expand and deepen their scholarly inquiry. To honor his memory, the Dewey family, friends, and the college have established the Bradley R. Dewey Scholarship Award, which is given annually to a faculty member who best exemplifies the ideal of a scholar whose research efforts reflect and inspire excellence and enlighten teaching. This year's Dewey Award honors the accomplishments of our colleague, Professor Stan Mertzman, the Dr. Earl D. Stage and Mary E. Stage Professor of Geosciences. So please join me in welcoming Professor Mertzman.
You may know that gentleman. We have something in common, and it's not your singing voice, and not mine for sure. Bono and I have in common, he's the lead singer, if you know, for U2. We both broke our elbows. I managed to have a compound fracture of my elbow this past summer, together with a punctured lung and a fractured rib. And simply, you can work with it. If you take on your physical therapy, it's amazing what you can recover. So this is a week later, I'm in the lab, and again, you may have seen a note out there that Bono simply was thinking that maybe he would never play his guitar again. And so my tweet to Bono would simply be, dude, you can do it. You've got to do that physical therapy like a religion, and you'll be back playing your guitar. The present is the key to the past. That's been around since the early 19th century. And you and I, we have a pretty good idea how our world operates. And there's some questions, but slowly but surely we're understanding plate tectonics, what happens when carbon dioxide goes into the Earth's atmosphere and so on. But what do you do when there's no record? What do you do when you go back before libraries existed, writing existed? How do you gather that information? That's what drives me. So sometimes there's a great similarity between a geologist and a detective. And in terms of that, sure. If you're in Hawaii or in the Azores, places where basalt lava flows on the Earth's surface, you know about Hawaii. Many of you have been to Hawaii, I would suspect. At least the older contingent in the front. You may have seen flows. And again, you can see it's thicker, it looks more clinkery. But if you see these kinds of activities, you know what's going on. The key is, can I interpret this 5 million years ago? Can I interpret this when this happened 25 million or 2.5 billion years ago? So my research involves 3 facets, and that's what I'm going to walk you through here. The first, and probably the one thing that I'm most proud of, is the geologic mapping. You put on a good pair of boots with 5-gram soles, and you take your students and you spend 4, 6, 8 weeks camping in the field, and you have a wonderful time really getting to know geology. You make maps, and a standard geologic map is 7.5 degrees latitude by 7.5 degrees longitude. So as you know, the latitude is a smaller circle, so as you go north, and it gets wider as you go south towards the equator. So it's not really a rectangle, it's a quadrangle, and that's where the term comes from. At 40 degrees north latitude, each 7 by 7.5 by 7.5 minute quad covers about 55 to 56 square miles. My students and I, we've covered 10 of these. I've got 3 on my bucket list yet that I'm still working on that I hope to finish. And in terms of Mount McLaughlin, it's wonderful. If you, like me, have a strong interest in volcanology, you can see here, there's volcanic rock everywhere you look on that photo. In the background, you have Mount McLaughlin, one of the Cascade peaks, and in the foreground, you have Brown Mountain. And you can see they have slightly different shapes, and simply, if you look at the rock on the right definitely looks sort of porphyritic, it has lots of crystals standing out, and the one on the left is really fine grained, pretty uniform. They produce essentially at the same time. Volcanoes are only about 8 miles apart. It goes to show you that these volcanoes, each one has its own independent plumbing system. They don't usually mix together, and each one is following its own path. Sort of like students, each one following his or her own path. And you and I have to identify them. We have to separate them one from another so that when I'm walking through the woods, I come across an outcrop, I can distinguish which volcano this particular lava flow happened to come from. That's what mapping is all about. So here, young geologists looking at trying to identify the minerals present in the rock and to provide a description. When you look at that rock a little bit close up, paperclip for scale, you'll see that this one is quite vesicular. One of the errors is people will sometimes say, well, look at those air bubbles. No, you just put a stake in my heart. There's no air, there's no oxygen that comes from volcanoes. The gases that stream out of a volcano would mostly be water vapor and carbon dioxide, sometimes a little bit of carbon monoxide, sometimes some sulfur dioxide to give it that rotten egg smell, but no oxygen. The oxygen you and I breathe all comes from the photosynthetic process. Beautiful, beautiful. You love this country. This is right on the Oregon-California border, just north, going up toward Crater Lake, which is in behind Mount McLaughlin. You and I are going to climb it right now. This is what it looks like in the very earliest of summer. Lots of snow. There are no surface streams here. All that snow is going to melt, and that water is going to soak into the ground to help resupply the groundwater table that a lot of ranchers and farmers use downhill for irrigation in this particular area. And so you can sort of see off to the left, there's a little bump, and there are a series of parasitic volcanoes that have grown on the margins. And those that sit right on the slopes are very similar to the major peak itself. Now, this is taken from a lake, and you can sort of see that something's happening. You can see the hump to the right. These volcanoes are notoriously weak. Any kind of significant earthquake activity, portions of that may collapse. And that's what you see there. The hump, you can sort of put that back into the major volcano and make it all one continuous part. We're going to climb. And this is part of the Sky Lakes Wilderness area. So you get out of the parking lot, about 200 yards, you're in the wilderness area. And you need to take a little bit of care because that means the Forest Service people, anybody coming to look for you is not going to be on a motorized anything. They're going to have to walk. And you and I are going to take a 5.5 mile walk to get to the top of the volcano. We're going to climb 5,000 feet vertical. This is what my students do when they go with me the very first day because they need an overview. Well, if you're going to need an overview, being up 9,500 feet in elevation, what a beautiful place to do an overview. This is also the Pacific Crest Trail cuts through here. So at night, if you're camping along the trail, you go out one day and you come back the next day and you just put your sleeping bag down or your blanket down, sleep on the ground, you can meet some interesting people. Sometimes I'll be out 2 days and never see another soul. Then I could be like Bono, and I can sing to my heart's content. Nobody but the birds and the little squirrels will hear me. Merciful. We're now up on the ridge. We're looking down at the lake that was in the foreground for that last picture. So we're up on this ridge, and now we're going to continue climbing. You're going to see big, blocky lava flows that came out of the crater like this. These are all less than 20,000 years old at Mount McLaughlin. So we would sample these materials because one of the things we'd like to know is what changes occur from the oldest, the lowest in this sequence of pancakes, to the most recent material. And what we'd like to do is to document each one of those as we go north up the volcano. So here we are, we're on the edge, right where we saw that big landslide. So here, you and I are right on this edge. We've already gone 3.5 miles, and we've climbed 3,000 feet or so, and we've got a little bit to go yet. So you and I, as we're going up that edge, you and I can see much thinner lava flows. Underneath it's all fragmental kinds of rock, and you can really see that material is going to be very porous. That water from the melting snow is going to soak in it, and it will move both to the west and to the east, supplying both the Medford Valley and the Klamath Valley to the east. But you can see it behaved as a continuous lava flow that looks very different from the ones that you've seen previously. Once we finally get to the top, you can see the youngest of the lava flows from the summit crater. So we've got a very nice stratigraphy that we have determined then all the way to the top. So you and I have collected a hand sample. We will send that back courtesy of UPS, and that's what you will start to work on in August when you get back to college before, if this is your independent project for 2 semesters. You'll plot that, you'll do chemistry in addition to looking at the minerals. And we always use these kind of XY plots. Silica across the base, the x-axis, and what we do is each one of those points represents a rock. It represents a lot of energy that you've spent preparing that rock to do that kind of analysis. There'll be clumps, and each clump might be a particular volcano, and you'd like to understand how one clump relates to another. And this happens 5, 10, 15 miles beneath the surface of the Earth. That's where the complexity enters, and that's where the detective work begins. So, what's the final product? A CD. And that CD will have a beautiful map that you can print at various scales. And in addition, it'll have a wonderful booklet written by yours truly. And what I get to do is I get to write a story. I get to incorporate the pictures that I take during the summer and weave it all together with photomicrographs and the chemistry. So probably the most rewarding part of this is that I've done 10 of these now with my students. So the students get a publication, and what's pretty neat for an undergraduate as a senior, maybe a first-year grad student somewhere, or working for dad or mom in a company, they get a publication for which their name will be on for all time eternal. 10 done, 3 to go. The second part of my work pertains then to NASA and the Canadian Space Agency. And right there, Dawn is the current vehicle that's in the asteroid belt. Dawn spent about 16 months circling then Ceres on the left. It sort of looks like a potato. And then it's coming up on, let me get this right, Vesta is to the left. Ceres is to the right. Dawn's coming up on Ceres. This is the latest picture that was taken a week ago, Friday, February 6th. And Dawn is slowly going to go into orbit early in March around Ceres. Ceres is the largest. Vesta is the second largest object within the asteroid belt. I'm perhaps more proud of that publication you see listed on top. Just came out last year. But Karen, my daughter, is my lab manager. And Julie Quinn is my youngest daughter. So to be able to publish with 2 of your own kids is a pretty unique opportunity. So it's pretty cool. We're using the electromagnetic spectrum. As you can see across in the middle, where you've got the beautiful rainbow colors, that's visible light. If you go to the left, ultraviolet light, shorter wavelength. You go to the right, you go to heat, infrared radiation. And so my students in my geology class this semester are using the petrographic microscope that you see in the middle of that photograph. And they're using that to identify the minerals that are present in these individual rocks in great detail. If you go to the left, there's X-rays. And we're going to use some instrumentation that uses X-rays to identify these. Chemists study minerals and rocks as well as geologists. And what they like to do is to simply expose minerals to ultraviolet, visible, and infrared radiation. They like to do that kind of spectroscopy on lots and lots of different things. Well, that's what spectroscopy is simply taking some part of that spectrum, UV, visible, or infrared, and bombarding a particular sample. Now, when they do so, what they'll do is they'll get a series of curves. Over on the far left, you see what's called absorbance, and that's what will be absorbed by whatever that target material is. To the right, you see transmission. So as that curve sags and gets to its lowest, that's where the transmission, that's where the transparency is going to be the greatest. You see something labeled olivine. And notice if you follow the olivine curve, it reaches its lowest point in G for green and Y for yellow. That's the color that olivine has. Any of the students here have taken intro geology, you've seen green olivine. That's why it's green, is that it has the best transmission at that part of the spectrum. You can see almandine garnet. It's another very common mineral, particularly for those of you who live down towards the Philadelphia area. Coatesville area, garnet is very common. and it has a reddish color. Notice that its curve is different from that of olivine. As far as chemists are concerned, that's what they want to do. But if you're going to do spectroscopy of Vesta, if you're going to do spectroscopy of Ceres, or the spectroscopy of Mars, you and I have to get together, the chemist and me, because I can take that mineral and then do chemical analysis. There we have a powerful tool, because we can do the spectrum, I provide the chemistry. Look at what we can do. We can have an indirect source. Okay, here's one more. For those of you who are in the gemstones, beautiful sapphire, often a bluish tinge. You do the study for sapphire, you can see that the bottom of that curve is right into the blue-green. It's most transparent in that ultraviolet side of visible light. So colors of minerals really are strongly related to those curves. The neat thing is we can do this 200 miles out. So all the things you hear called land satellites, that's what they do, is they bombard the Earth in a small strip, as you see in my model here, and simply that radiation will be reflected back. So we can map the surface of Mars, we can map the surface of Ceres and Vesta and so on. And then using the algorithms determined from the chemistry that we're going to determine, we can tell what's there. Now we can see a lot about simply what the minerals are. Are some of these elements oxidized because of certain conditions, oxygen-rich material? But we can do a lot of different things with that information. Once a year, science will put together a pretty large compendium that will give you the latest data concerning Mars. We worked on the Canadian Space Agency, putting together a library, trying to connect then the spectra that chemists provide with the chemistry that I'm able to provide. This is what it looks like on Mars. Again, on Mars, it's one thing simply because it can't weigh much. So we're looking at 5 pounds. Miniaturization is the key. They want instruments to go, they'll give you the weight. If you can make that weight or lower, sounds like wrestling. If you can make that weight or lower, you're okay. If you can't make the weight, you don't go. It's very, very simple at this point in time until they get a larger booster rocket. You will get a spectrum back, and that spectrum is coded for the various elements that you will find in that material. That's the raw data, and now what we have to do is translate that into what the mineralogy happens to be on the surface of Mars, the surface of Ceres or Vesta, wherever we're living. This is what I get in the mail. This will come FedEx, stainless steel box. You cannot destroy it, short of running it over with some kind of giant, enormous vehicle. And in that box are these things. And the last one, we're up to 1610. Karen and I just sent 1610 back last week to NASA at Johnson University. And in here will be the most eclectic group of minerals, rocks, whatever they deem that they need chemistry for, they send it to me. And so we're up, as you can see, we're up to 1610 these days. We have to crush it. So in here we have one, what's called a molite grinder, where you can crush material here. We split it because you never want to simply have one and only one, because if you're like me, you could trip, you could sneeze, and all of a sudden somebody's important sample just was vaporized or contaminated in some way. So at best we will split it into half, and if we've got enough material we can split it a couple of times, so we always have something to fall back on. We can crush it even finer. You want this down to tablet-sized powder material. The smaller the particle size, the greater the reactivity, the greater the surface area. And so that enables that material then to react more readily. You'll see why. We want to know what the volatile content is. And in terms of that, we have a muffle furnace, 950 degrees centigrade. So at 950 degrees centigrade, we're going to heat this material. We're going to put it into one of these ceramic crucibles that is nice and clean. And I'll weigh out exactly to 4 decimal points what the weight of the material in that furnace, in that sample. Put the basket in the furnace. Let it be in the furnace at 950 to 975 degrees for an hour to an hour and a half. And then that comes out and goes in a desiccator. And then we will reweigh that material once it has come to cool temperature again. The difference is going to be proportional to the volatile content. The one thing that's you got to watch is the Earth has 20.5% oxygen in the Earth's atmosphere. So that means things like iron, manganese, those particular elements will oxidize. And when you oxidize, you gain weight. So there are 2 things going on in this step here. loss of volatiles, and gain of weight due to oxidation. That demands then, I'll be patient. That demands that we do a titration. And that titration is to determine the amount of ferrous iron or manganese ion in that material. And so here, the safety officer always cringes because if you look at the beaker in the lower left corner, it has HF on it. And safety officers and HF don't go hand in hand. But to dissolve a rock, you need some extraordinarily strong acids, a mixture of HF and sulfuric acid. That will dissolve many things, but usually there will be the most resistant minerals left. So you heat that material, you add the reagents, and then we're into the Henry Ford method. You can see that there are 10 of these that will eventually be on the hot plate. And so you do them in packages of 10 or 12, depending on how many crucibles we have available. 2 techniques down, 2 to go. You can see to the right, you can see a platinum lid and a platinum dish. We're going to make the glass disc directly below it in this technique. To the left, you'll see a briquette, and we'll simply weigh out reagents to do this. That's what they look like in scale. To the right, we will determine the major element chemistry, and we'll talk about that in a moment. To the left, the trace element constituents. On the left side, we are diluting this to make this glass. It's a 9-to-1 dilution, precisely. All my standards are made up the same way. To get this data, I've got to do about 50 to 55 standards to make sure I calibrate for silicon, for aluminum, all the elements that are present in here. And then you get to play with fire. My students in my course this semester, we're going to do this afternoon. And so it'll be interesting. That's exactly what we're going to be doing. And so your sample is going to turn into a puddle, lava, magma, if you will. And eventually you've got to get it. Can you rub your head, and what else are you supposed to do? Tap your head. I can't remember what the whole thing is, using both arms. Rub your belly, thank you. I needed all the cues I can get. But that's what you have to do here. You can see in the lower left, I'm holding the pan over a burner on the left side, and I'm doing this with my right hand, so you need to be semi-coordinated. So in terms of this, I'm tilting it over, and here you're going to pour into that pan, just as you see here. You're going to cast the glass disc. And then success, unless I drop it. Okay, and that's happened. Everybody makes mistakes. You can't really hurt anything. You might start a fire, but you can't really hurt anything right here. So when you're done, and there's Karen, she's as good as I am. We have done this for about 15 years now, and this is what it looks like in terms of the backdrop. And what we're going to do is determine that whole slew of elements right there. And you can do this for soils. You can do this for lots of different materials in terms of telling exactly what they're made of. There it is. Glass disc comes right out of that dish. It doesn't stick, and you're ready to roll. You're ready to roll. 9-to-1 dilution. That means there's not a lot of stuff in there. A lot of elements aren't very abundant, 1 or 2 parts per million. That's what we have to do here. Karen's pressing this material out, and there's the mold. 50,000 psi she'll generate to press out that trace pellet. It's the material on the left, 7 grams, 7.0000 grams, and it's got a little bit of binder, 1.4 grams, to hold it all together into a very tight pellet. It's infinitely thick to the X-rays. X-rays can't penetrate through that material or we'd have a problem. Now, in terms of doing it, this is, and again, depending on your familiarity with the periodic chart, you may not know all those elements. But what I'm after here, some of those elements are key. Imagine a box with 1 million ping pong balls in it. I want to know whether there are 3 red ones or 4 red ones. You can do it. You can do it. And that's what X-ray technology is all about, is to be able to measure both with that precision and then also with get that same kind of accuracy. So these elements will help a geologist work out how that material originated. That's the instrumentation. To the left is an X-ray diffractometer. That's like taking your fingerprints. Every mineral has a unique X-ray pattern, just like you and I have a good set of fingerprints that will distinguish you from me and so on. That's what the left-hand instrument does. The right-hand instrument is X-ray fluorescence. They both use Bragg's law, N lambda equal 2D sine theta. They both operate after that. Left hand, identify the mineral. Right hand, what's the chemical composition? As you can see, we're set for doing lots of samples. We can load about 144 of these. What's really satisfying is to go out of here on a late Friday afternoon heading for the gym and knowing that that instrument is going to run over the entire weekend. Now, if I go out of here thinking that, that means it'll quit before I get out of Mazer parking lot. Because this isn't supposed to make mistakes. That's what the good Dutch and Germans who make this instrument tell me. It knows me. And so if I go out thinking like that, so I have to play with my brain. But I'll come back Saturday morning, I'll come back Sunday morning just to make sure it's still, running at those points in time. That's what it looks like up close, and it has a sample changer that will simply has a pneumatic. It'll pull up the glass disc, move it over to the cup, put it in the cup, load the instrument, and then do the same thing. For the glass disc, it takes about 15 minutes. For the trace pellet, it takes about 1 hour and 10 for each one of those. So having it run overnight really does expedite things. The last one is even more fun than working for the NASA and Canadian Space Agency. You get to work with a lot of local companies who knock on your door when something isn't going right. And Armstrong is wonderful for this. And Armstrong has a plant that they make fiber. And this mineral fiber is literally just glass fibers. And they use it for ceiling tile. So all the ceiling tile that you encounter and some of the floor tile comes from the mineral wool that they'll create here. It's a spectacular place. Karen and I went down a couple years ago. They invited us down to show us exactly what they're doing. And if you like heat, it's a wonderful place. So they have a series of furnaces. Here's one right here. And if you're into experiments, I'm used to experiments where you weigh up meticulously 0.5 gram. These folks get to do experiments where there are tons of stuff. And if they make a mistake, they just have a lot of crap. But in here, it's really interesting to see what they produce. It's on a scale that's just unbelievable to a geologist. Maybe not to a chemist, but to a geologist certainly. But giant electrodes. There are 6 of these electrodes that come down. I found out later that Millwood, where this plant is the #1 electrical user in the state of West Virginia. And so when these things are running, it's absolutely amazing. So what's cool for me, all I can think about is magma. All I can think about is lava when I'm looking in this door, looking at this experiment going on. And again, well, back there, you can sort of see in the upper left corner, you can see the chutes, because that's where the slag comes in that they use as their ingredients. Now, what's really informative is this stuff comes in giant tractor-trailer loads of material. And so, they don't often sample a tractor. How do you sample a tractor-trailer load of slag? What do you pick? That alone is a challenge in terms of trying to figure out what it is that you take out of this load of slag that's being dumped that they're going to use as ingredients. And so in terms of the different compositions, that's what they're going to use to make their particular mineral wool. In terms of the composition, that's going to determine the acoustical properties, and so on and so forth. So if you change the composition, you change what the net result's going to be. And when they finally get it hot enough so that it can pour hoi hoi by any other name. Its chemical composition is nothing like you'd ever see at Kilauea or Mauna Loa or in the Azores, because the slag that they're using is very rich in manganese. And so it's always a challenge to provide them with accurate and precise data. So you can see these gentlemen here. You get close. If you like to play with pohoi hoi, this is the place to go. You can work 8 hours a day and get to play at the same time. So you can see it coming down. Now, again, you can see that it's left the furnace. It's cooling the whole way. It's losing temperature all the way down. That can cause you a problem, because if you go to Europe, the feature that's running on is called a launder. And that the longer it is, the more temperature you lose, and that means the more viscous that lava is going to become. It's going to become thicker and pastier. Well, that's going to change what happens here. It goes over that edge right there. The only way I could get a picture was when they're not running. It goes over that edge, and right here, right there, is a spinning disk. And that molten stream is going to hit that spinning disk, and it's going to go to fibers. And that's what they're going to produce. So they've got a rotation. How fast do you spin that disk? At what rate do you enter the magma? Because all that's going to govern the fiber length, the fiber diameter, and how much stuff they get that's called shot. It really looks just like BBs, and because they want to minimize the shot and maximize their fibers. So that's what it looks like when you look through there. They let me, because their safety officer went someplace else. So when the safety officer left, I was able to get in, and luckily I didn't burn my gray hair nor singe eyebrows in terms of getting to a place where I could look in. But you can sort of see there's a disk that's rotating in there, and that hot magma is coming down and hitting that and spinning. And what it generates is that. It generates those fibers, and they bale this. Just if anybody here is agricultural in background, this is like baling hay. I remember as a kid, more bales than I ever wanted to see. But in terms of this, I'm not picking this bale up, as you'll see in a moment. So they come through, that they are put together, forklift to lift them up, and 836 pounds in that bale. That'll go into a truck or a railroad car and end up then at a manufacturing plant where they do ceiling tile, in some cases floor tile, and so on. But that's the starting ingredient for that material. Again, change the slag from a different plant. If you change the ratio, you change the chemistry. And that all just feeds itself down to their acoustical properties, how well the tile holds together, so on and so forth. So, XRF, X-ray fluorescence spectroscopy. It really informs the ability of a person to put together the best geologic map present, whether it's on the Earth, it's lunar, Martian, on down the line. It's extraordinarily helpful in planetary science, and that's a burgeoning field. And so be able to interpret what the surface of Mars, the surface of Vesta happen to look like remotely from here is great. And whenever there is a return mission from Mars or a return mission from one of the asteroids, it'll be fantastic to actually test. Were we accurate? Were we precise in our chemistry, having done it remotely? It'll be really interesting to see how well we have done, never having set foot on the moon or Mars or Ceres. And lastly, you just never know what will come in the door from Armstrong or Isolitech or North Carolina State or the Idaho Geological Survey or the state of Oregon. All of those folks send samples here to F&M, and you have no idea. Professor Mertzman, this particular material is not behaving exactly right. Well, what's that mean? Well, it doesn't pour right. Can you tell me why? I'll determine the chemistry and do the best I can, and that's what we do. But if you're curious at all, it's a wonderful place to be. Very seldom do you get a chance to say thank you, which I can do here. If I start doing names, that's bad, because you'll always forget somebody, and I don't want to hurt feelings. But I'd like to thank my department and the college colleagues that I have out there. Members of the provost's office, one of whom will remain nameless, but occasionally I have to knock on a door because something broke and I currently don't have the money to pay for it. And he'll know who he is, but it's been very handy. He saved me a couple of times, and thank you, Alan. The college staff, there are some wonderful folks here who keep Hackman running, and they do a wonderful job. There's a wonderful person in the warehouse that always gives me a call when a package has shown up from a company or a college who wanted their data yesterday, and they're already calling me the day the package comes because they want to know if I've got data for them, because they have no clue what the procedure is to get the numbers. In addition, I want to thank my very tolerating family. They're all scientists. You can see my son Michael, my daughter Lisa, Karen to my right, your left, my youngest, Julie, and you can see a little one who just wasn't about to be without mom for a second. And then you can see the disembodied hand as well. And this is a couple of days after the fiasco on the bicycle. At least Bono, hit another cyclist. I happened to hit a hidden pothole, but let me tell you, I'll never be on my bike without a helmet, because otherwise I don't think I would be here, because my helmet was torched in that fall. And the human body is interesting, because I remember starting to go over the handlebars, and I don't remember anything else until I started to get up off the pavement. And I hope I never remember exactly what that was like. This is the whole cast of characters here. There are 10 grandchildren in there. I love the one with the popsicle. We were definitely, bribing somebody to do okay here. And I'm not going to say anything about the next one. I'll just leave that unsaid. But it's close to Valentine's Day, and you get tired of insipid cards, so I thought this was better than that. If there are any questions, that would be fine. Thank you.
I took a class with you, and I know from first-person experience that you're like the Energizer buddy. And I just wonder if you ever have to carry any of those students up that volcano.
It's always interesting. And again, I should give a shout out to the Keck Foundation, because the Keck Foundation funded a number of these summer research projects for students. And sometimes some students wouldn't make it. They'd give it their best shot. But it's, at least if we're climbing McLaughlin, it is literally 5.5 miles to the top, and it's about 5,000 feet to get to the summit. And for somebody who has not spent a lot of time, exercising or whatever, that can be pretty arduous. And we always strive to get everybody to the top if humanly possible. But sometimes it isn't. But again, because you need to get up and down in one day. If you're out here early, it's like a mosquito gauntlet as well, because it's fairly wet from the melting snow, and they're all coming out. So you want to keep moving, because if you stand still, you're just simply breakfast, lunch, or dinner, whatever the time happens to be for those mosquitoes. Later in the year, it becomes a little more tolerable once all that snow is melted. But yeah, no, it's some years we get everybody, and other years not. Again, this country here is fairly dry, so if you're on the east slope of the Cascades, you may only see 12 to 15 inches of moisture. It makes farming and ranching a little dicey. Irrigation is quite significant for them to grow enough crops to feed their cattle.
Hello, I'm Annalisa Cornell. I'm a mathematician. Thank you for some NSF advice a couple years ago. That really helped me. But I was actually going to ask you about, you said something that sounded to me sort of biological about a mountain. That is, you said it had parasitic volcanic growth. So I was wondering if you could tell us more like gossip about the lives and times of volcanoes.
Brown Mountain, which was in the foreground of one of those pictures, which was a separate structure, and then you went to Mount McLaughlin. If you have one volcanic either plug, think of it as a soda straw, that comes up and is on the flanks of an existing volcano and is producing lava and rock that looks quite similar to the main edifice itself, then that's where the term parasitic comes in, because of that similarity. If it's very different in terms of its both mineralogic and chemical makeup, then the word parasitic sort of falls out. But it's simply, as you say, related to biology, because it's a smaller structure as like a pimple on a bigger structure. And so often, not always, often there will be these subsidiary, secondary structures that are producing exactly the same kind of material as the main volcanic crater happens to be emitting. Steve.
Hi, Stan. How many individual lava flows did you and your students map out there?
To answer your question, the range of the age of the rocks that we worked on for these 10 quadrangles range from about 22 to 23 million down to less than 20,000 years old. And within those 10 what turns out to be about 550 to 600 square miles. Within that structure, there are probably 250 to 275 individual volcanoes. And so there's quite a complexity when you put the whole thing together in one area. Individual lava flows, thousands.
Well, my real question is, were there structural or stratigraphic problems that you were able to solve only by using the trace elements? Did you have to bring pieces back and analyze to figure out geologic?
Oh yeah. Every individual lava flow is sampled multiple times. The process a geologist refers to as correlation. You're trying to correlate one outcrop that's not connected to the next one. And so you might go a mile or two and you say, wow, that looks pretty similar. Well, just because it looks similar doesn't mean that it's going to be exactly the same kind of lava. And you can use, as you're pointing out, you can use the strontium or the yttrium or the niobium. You can use it as a tracer because for individual volcanoes, there are usually just limits of variability for each one of those individual elements. And so by using that variability, you can often connect things up. Because you can imagine if a lava flow erupted here in Lancaster County, it's not going to cover everything. It's going to flow down the low spots. So wherever you've got a creek or a drainage, that lava is going to collect down that drainage and flow following that stream bed downhill under the influence of gravity. Now, what's always interesting, because in typical layer cake geology, if you're the last pancake in the stack, you're the youngest. If you're that first pancake down here, you're the oldest. Okay, so now you cut into that stack of pancakes. You take your piece out, and now you've got that wedge missing. Lava erupts. It flows right down that wedge. So it's lower down, but it's the youngest of the bunch. And so that kind of inverted stratigraphy is the bane of a field geologist. If you're into regular sedimentary geology, then you can pretty much rest assured, unless there's faulting or some other kind of complexity going on, that higher up is younger, lower down is older. But in volcanic terrains, it's a challenge. And there are times the only way you can work this out is by using age dating. I used to go back to my alma mater until the person moved and do potassium argon age dating. And it was so exciting because you would, at your time, you could do 6 of those in a day, and then you had to tear the system down and then reload. And so you would work 24 hours straight, and you would get 6 numbers. And those 6 numbers, that would really inform you. You'd be so excited. You'd be putting in the computer, and here comes that number out. Does it fit with your hypothesis? Yes, it does. And other times where you look at it and say, what was I thinking? Back to the drawing board, because that number didn't fit into what I thought it would be. And that would be a most exciting time in terms of seeing that go on. And sometimes it works, sometimes it doesn't. And sometimes you need more detailed information because the information you have at hand isn't either sophisticated enough, isn't in detail enough. You don't have the total element chemistry, because you notice between the majors and the minors, I'm still leaving more than half the periodic chart unaccounted for. And so there might be stuff where we're missing. Jacob.
Hey, Professor Mertzman. Just a question from a curious student, but do you plan on doing any other trips to Mount McLaughlin with students over the summers?
Right now, you reach a certain age where at the present point in time, yes, I will be back at Mount McLaughlin this summer. But things happen. And so, after that bicycle accident last June, that I didn't get in the field last summer. And so the itch is doubly strong, so to speak. There's just something about being in the woods, walking, doing geology, that's just fantastic. And so the powers that be, if they let me, I'll be there. And I'll be to the top, because that's sort of the thing that you start your summer with.
Hey, Stan. I'm Sam, a senior geoscience major. I had a question kind of related to that. Why did you choose to study in Oregon? You talked about the Azores and Hawaii. There's millions and millions of places on the surface of the earth to choose from. Why did Oregon speak to you?
Good question. I have to really think back. My PhD thesis was in the San Juan Mountains of southwestern Colorado. And at that point, I went to the Smithsonian Institution for a postdoc for 1 year before coming here to F&M. And the person at the Smithsonian was very interested in a volcano called the Medicine Lake volcano that's right on the California-Oregon border. And so I got my PhD in mid-August of 1971, and then a week and a half later, I moved to Washington, D.C., and a week and a half after that, I was driving to Northern California to start the field work before the snows really sort of came in. And that's what it started, because I worked with him in conjunction with that on some very young glass flows that are only about 1,000 years old. Lots of obsidian, all kinds of really neat stuff. Indian camp spots around there where you could see where they were napping for Indian arrowheads and blades and all that. So it was, in terms of archaeology and geology, it was pretty neat because there were archaeologists working on it. It was pretty neat to listen to them talk, and they really liked to listen to me talk in terms of the geology and all that. So it was really symbiosis in its best sense. And it started there because as I was there, I found out that all the structures and all the area from Medicine Lake on north to Crater Lake. Crater Lake is as far as I've gone north from here. It's about 75 miles as the crow flies. If you've never been to Crater Lake, I would encourage you at some point to be there, walk down to the lake, take the Park Service boat ride around there, and then climb your way back out. But if you ever wanted to see a three-dimensional view of a volcano, because Mount Mazama exploded about 7,000 years ago and provides you a cross-section, just like you would take a knife into a layer cake. Nature has taken a cut in through that volcano, and you can see the interior very, very nicely exposed. And so it's a spectacular spot. And again, I try to get all my students up there for their day off. Do the laundry, very early in the morning, and then we go to Crater Lake, do the boat and all that kind of stuff, and then I salve them by giving them a decent dinner that's not something that we cooked ourselves, and then back to camp to start it all over again for the next 6 days. Anyway, it was a long story, Sam, but that's where it started. Anybody else?
Hi, Stan.
Hey, Paul.
So I have another biographical question.
Sure.
You mentioned hay bales.
Yes.
Or some familiarity with hay bales, and I wondered how you ended up even getting into geology to begin with. And some of you will take solace in this, I was not the best undergraduate student you ever want to see. When I was a senior in high school, I had a chance to go to the Air Force Academy. And the thing I wanted to do, maybe that's because I baled too much hay for cousins who I would get farmed out by my parents. And I spend a week with this cousin, a week with that cousin. And every time, it was always baling hay. Come on, I'm scratching just thinking about baling hay. Because, boy, it just went everywhere. But in any event, so spent that time doing that. And I really wanted to fly. And so I was smart enough in high school, and the local politician, I was able to get nominated to the Air Academy. Yes. Well, Wright-Patterson Air Force Base is right outside Dayton, and that's where you had to go to do the physical, 2-day physical. And the first day, oh, yeah, this is cool. Second day, do the eye test. You can't be colorblind and be a pilot because you can't see those numbers with all those colored dots. I used to be an experiment for Fred Owens going over there to do some of his color testing and all that, and that was bad. So anyway, I just remember this guy come over the intercom because he says, bring this in on runway, and he gave me some number, and I'm thinking, what number are you talking about, dude? I don't see a number. And so flip a coin mentally, land on this one. He says, sorry, son, you're going to be in the second seat. You're not going to be a pilot. It took me 6 months to recover from that. And then I moved on to baseball. And so I didn't really get serious as an undergraduate until I was a junior. And luckily, I did well enough my junior and senior year to get a fellowship to go to grad school. But so if some of you are sitting out there thinking about late bloomers, it took me a while to get my act together. And again, I did more chemistry as an undergraduate than geology. But geology is pretty cool because if you read their graduate catalogs, it'll say, geology majors certainly welcome, but if you have a strong interest, you're a chemistry major, or you're a physics major, or you're a math major, or a bio major, hey, apply too, because you can always apply those sciences to understanding the Earth. And so geology is pretty welcoming in terms of lots of different specialties. So you too can be successful if I can be, let me tell you. Sir.
Tim Brixius, Communications. I was just curious, looking at this picture that's been up there for a while. Besides your marriage, are there places where geology and sociology intersect in terms of their research?
From what I hear, and it's really cool because Carol deals with animate objects and all that, and I deal with inanimate objects entirely. So the conversation, I learned so much. I think there's a course called Sociology of Disaster. And so, that would be an interesting one to teen teach, because boy, do I have disasters. All I can think of is Pompeii, tsunami. There's just a whole variety of geologic issues with that. And so, it makes for interesting conversation. Death and that would be the course that I would teach, death and destruction. I'm not sure. I'm not sure you could spin that as a connections course, but I'm not sure who would be coming to listen to death and destruction. That'd be sure.
Stan, I have a question about that photo. If that's not San Francisco, then I don't know. But when was that taken? Because I don't see the big TV tower. Maybe it's hidden by fog.
Could be, but this isn't that old, I don't think. I think this is maybe 2004, 5, somewhere in there.
Well, there must be fog in there because that big TV tower up on Mount Davidson or whatever it is.
Steve should know. He taught at San Francisco State for a while, right? So in terms of San Francisco Bay, I'm on the north end of the Golden Gate right here looking back towards San Francisco. Pretty spot. Wendy.
I didn't announce myself before. Wendy Baker Davis, ITS, Technology Support Services. I actually had a question about how do you clean the rock crushers and all the different machines that you use that you described, because how do you get the traces of what was there before out before you do the next thing?
I should invite one of my students up to do that because the one-word answer is meticulously. Because again, the last thing you want to do is have contamination. And so, again, one of the most common elements that you and I will be analyzing for would be alumina, Al2O3. And so all the grinding vessels that I use are lined with ceramic. You're going to contaminate no matter what you use, and you just have to live with it. But if you contaminate with a particular element, because the stuff that's made there is essentially 99.99% pure, so you're down to 100 parts per million of a contaminant. If I'm going to contaminate anything, let it be alumina, because there's virtually alumina in everything you and I are going to look, except carbonate rocks. So if somebody's into carbonates out there, then again, that's going to be a trace I'm going to add. But for most of the common rocks and soils, alumina is in there. Your theory is not going to change if you start with 10 and you end up with 10.1% Al2O3. That's not going to change your theory. On the other hand, there are some crushing devices that are made out of tungsten carbide. And you can't get tungsten carbide pure. There's going to be titanium, other high field strength elements like niobium, zirconium, and so on and so forth. And so in other expensive, that's more expensive than ceramic, you have a problem with contaminating elements that I am highly, highly interested in, that I can use to distinguish one origin in terms of the magma versus other origins in terms of looking at those concentrations or ratios between two elements. So that's why all the stuff in my lab, and this is not true across the country, because some people will still use tungsten carbide, and I'm totally unclear as to why. But we will use that alumina simply because it's hard, it's tough. The only Achilles heel is that it's brittle. And so if you drop it, it's a $3,000 mistake. If you let that mullite grinder come up and slap against the other one, it's going to crack. There's about a $2,000 mistake. So again, it's expensive to keep everything both running and then replaced in top notch. But cleaning, you know, somebody said that cleanliness is next to godliness. Way beyond that. Way beyond that. Cleanliness is absolutely essential to anybody who's into analysis.
I'm curious if you can share with us what some of the students you've worked with over the years are doing now in their own careers.
Oh, thank you. One of my early students, I've got I've lost count. 17, 18 students have gone on to get their PhDs, and they're scattered across the country. But there is one faculty member here at F&M, and he's a member of the faculty council right now. But Bob Walter, Dr. Robert Walter, was one of my students in Northern California. And he spent a number of weeks camping with me, and undoubtedly I'm not going to hand him the microphone because he would have some stories that he could probably regale you with that I just soon leave buried somewhere. But no, I've got a number of students. And the other thing, besides F&M students, and you're a good bunch, because originally when I came here, I was coming here for 1 year because I went to a research university. And if you go to a research university, the only way you're going to be, quote, successful is if you go to another research university, which means I'm going to teach one course a year, and I'm going to do research. And I had some pretty poor teachers. I had some good ones, but I had a number of poor, especially who would talk to the board as they're lecturing and talking like that, and you would just copy down the notes because there was no human interaction with the person whatsoever. And so when I came here, it was refreshing because F&M is an interesting spot. It demands good teaching, fine, but it really strongly encourages you to be a good researcher and publish your data. And that, for me, was the sale point, is that you want the best out of me in two different worlds. And I'm lucky enough to be in a field that I can link the research with the teaching. And so, you know, I change my notes every semester. I add this, I do that. And so everything tries to stay, you know, up to date. That's, for me, that's why I've been here the whole time, is F&M has been very, very good to me. I wouldn't change a thing. But it encourages the best in me, both from teaching and from research. And that's what it's all about.